Hi everyone. Okay, so good morning here, good morning to all. So we are going to start a subject here, analog circuits. Okay, so in the previous sessions here, in the previous session we have seen how to represent the equivalent model of a diode, yes or no. So we have seen about a piecewise linear model, right? Okay, so I have explained what is the need for a piecewise linear model and all those things in the previous session. So if you directly take the diode and if you want to analyze the circuit here, if you want to analyze the circuit directly, that means exact analysis. Suppose if you take the circuit, let us say this is V in, and here you are having resistor, and here you have connected a diode, right? Okay, so the current that is flowing here is ID, the voltage drop across diode is VD, okay, and the voltage drop across resistor is VR. So we have taken this a simple circuit and we try to do the exact analysis here. So that means through exact analysis we try to determine ID. So we got what here? We got some nonlinear equation. So solving that nonlinear equation here, is very difficult here. Okay, so that's why we have developed a piecewise linear model through which we can replace the diode. With linear elements here, like you can replace the diode with what? So I have explained that piecewise model here. You can replace the diode with some constant voltage, that is cut-in voltage V gamma, and a resistance RF, yes or no? Or you can approximate further and you can replace the diode only with the cut-in voltage, and you can approximate further and you can replace the diode only with short circuit whenever it is operating in forward bias region. Okay, so these things we have seen here. So once we replace the diode with this piecewise linear model, then the circuit is going to become what? The circuit is going to become a linear circuit, and the analysis with respect to linear circuit is very much simple when compared to analyzing the nonlinear circuit, right? Okay, so if you do the exact analysis, then the equations that we are going to get in this circuit will be nonlinear, and analyzing that nonlinear equations is somewhat difficult. So we have, by using piecewise linear model, we can replace the diode with some cut-in voltage and forward resistance. So if you replace the diode with these things, then the circuit is going to become what? Some linear circuit. Then the analysis will become very much simple. Okay, so whatever the analysis we are following here, whether you are following exact analysis or you are following approximate analysis, that is piecewise linear model. Okay, in both the cases the results that we are getting is almost what here? Is almost similar. So that's why instead of going for a exact model, we can adopt what here? A piecewise linear model in order to analyze the circuits. Okay, yeah. So what I have said in the previous sessions is, if suppose the diode is operating in forward bias here, it is operating in forward bias, that means let us say VD is greater than what? Is greater than V gamma, and RF, forward resistance RF, is not equal to 0, So in this case, how the graph will look like here? The graph will look like in this manner, right? So this is ID, this is VD, so you will get the graph like this. Okay, so this is nothing but V gamma. So this is slope is equal to what here? Slope is equal to 1 by RF. Okay, I have explained all these things here. So whenever VD is greater than V gamma and RF is not equal to 0, okay, so we can say the diode is operating in forward bias region. In this case, you can replace the diode with its equivalent model, that is nothing but what here? With V gamma and forward resistance RF, right? Okay, yeah. Next what is another approximate model here? So you can this is VD, this is ID. Okay, so now so now you can keep V gamma as it is, that is the cut-in voltage. The cut-in voltage is same here, the cut-in voltage is same. Okay, so now if suppose if I move this curve here, if I move this line like this towards if I move this line in anti-clockwise direction like this, then what will happen here? Its slope is going to increase. Yes or no? Its slope is going to increase further. Okay, and if you make a straight line, then the slope will become what? The slope will become infinity. So if the slope is becoming infinity, means the forward resistance offered by the diode will become what? Will become equal to 0, right? Okay, so this is another approximate model here. So here slope is what here? Here slope is equal to infinity. That means 1 by RF is equal to infinity. This implies RF is equal to what here? RF is equal to 0 ohm. RF is equal to 0 ohm. So here we are having only V gamma and RF is equal to what? RF is equal to 0 ohm. Right. Okay. So in this case you can replace the diode. In this case you can replace the diode with only V gamma here. Here RF is equal to 0. So you can replace simply with V gamma. Okay. So here VD is greater than what? VD is greater than V gamma and RF is equal to what? RF is equal to 0 and the diode is operating in forward bias region. So in this case this is the equivalent model. So next one, what we have seen, next one. So if you just shift this curve here, if you just shift this curve towards what? Towards this origin, then what you are going to get? Tell me what you are going to get. So this is VD and this is nothing but ID. Okay. So that means I am assuming the cut-in voltage of the diode is 0. The cut-in voltage of diode is 0, and whenever cut-in voltage becomes just greater than 0 here, then the current that is going to flow, through the diode, I am considering it as very, very large value here. It is increasing steeply. Okay, so that means the slope is becoming infinity. So this is ideal model here. Actually the current cannot go up to infinity. Yes or no? We are going to connect some resistances in order to restrict the flow of current, right? Okay. So this is ideal model. So this here you are having still slope is equal to what? Still slope is equal to infinity. That means RF is equal to 0, and here you are making V gamma is also equal to what? V gamma is also equal to 0. Understood? See, it doesn't mean that whenever you are having, if you are having a diode like this, okay, and if you connect some resistor here, okay, and if you don't connect any source here, okay, here 0 volts, here also it will be 0 volts, right? Because there is no current initially. So since here it is 0 volts, here it is 0 volts, the drop across this one is 0 volts. So in that case you may ask, sir, since it is 0 volts, can we replace the diode with a short circuit? No, you cannot replace like that. Okay, just cut-in voltage, just if it has to become, if it becomes just greater than 0 here, then only the diode will go to on position. Only in that case you can replace the diode with its equivalent model, right? Okay. Okay. So now see here. So in this case you can replace the diode. The equivalent model of the diode in this case is just with a short circuit here, Now here VD, that is V gamma here in this case V gamma. Here in this case V gamma is equal to what? Is equal to 0, and RF is also equal to what? RF is also equal to 0. So in this case you can just replace the diode with a short circuit, So this model we call it as ideal model here. This model we call it as what? Ideal model. And this one we call it as constant voltage model. Okay, So we have seen this is in forward bias here, forward bias region. So this is the equivalent model of the diode, equivalent models of the diode whenever it is operating in forward bias region. So depending upon the given data here, depending upon the given data, we have to use the equivalent models. See, suppose if they have not mentioned anything, if they are simply saying ideal diode, means just replace the diode with short circuit whenever it is operating in forward bias, right? So if they have given only cut-in voltage and if they have not mentioned anything about the forward resistance, then consider the RF value, consider RF value is equal to 0. Okay, so RF is nothing but forward bias resistance here. Okay, consider that as equal to 0. So if they have mentioned both cut-in voltage as well as what, as well as RF, then you have to use this equivalent model, right? So depending upon the given data, we have to replace the diode with its equivalent model, with its equivalent model, right? Okay. Okay, yeah. So now whenever it is operating in reverse bias here, whenever it is operating in reverse bias, that means if the voltage across the diode is less than the cut-in voltage, so here this voltage is less than the cut-in voltage. So in this region the current is what here, the current ID is equal to what, ID is equal to 0. That means there is no current flowing through the diode. Yes or no? So that means in this case you can replace it with what? You can replace it with open circuit. So here the diode is operating in reverse bias here, reverse bias. Similarly here also, if the voltage is less than V gamma here, if the voltage is less than V gamma, so it is, if it is operating in this region here, in this region, so here also ID is equal to what? ID is equal to 0. That means there is no current through the diode. So in this case also you can replace the diode with what? With open circuit. So that is reverse bias whenever it is operating in reverse bias. Now here also, so before V gamma the current in the through the diode is 0. So that is ID is equal to 0. That means you can replace the diode, you can replace the diode with open circuit in reverse bias. Okay, so once the voltage across the diode here is becoming less than cut-in voltage, okay, you can replace the diode with open circuit, and here also you can replace the diode with open circuit. And here if suppose the cut-in voltage is equal to 0 here, that means if the voltage across the diode is less than 0, then you can replace the diode with what? Diode with open circuit, right? Okay, so these are the equivalent models of diode here. These are the equivalent models of diode. Okay, so I have already explained all these things here in the previous session itself. Just I have revised all these things now. Okay, okay, yeah. So next okay. So next we are going to study about rectifiers here. We are going to study about rectifiers. See, first of all here my aim is I want to convert a pure AC signal here. I want to convert a pure AC signal to pure DC signal. I want to convert pure AC signal into what? Into pure DC signal. Okay, so what do you mean by pure AC signal here? What do you mean by pure AC signal? So that means the average value of pure AC signal is always equal to 0. So if you are determining average value of any signal, that is going to give you what? That is going to give you the DC component that is present in the signal. So for pure AC signal, average value is equal to 0 means the DC component that is present in the signal, is equal to what? Is equal to 0. There is no DC component that is present in pure AC signal. Okay, and what are the properties of pure AC signal here? What I have told, it is going to have, if you are talking about voltage signal, okay, if you are talking about voltage signal, so what so for half of the time period it is going to have one polarity, yes or no? So for 0 to T/2, and for the next half cycle it is going to have opposite polarity. Here it is having positive polarity and here it is having negative polarity. So whatever the shape that you are seeing over the half of the period, the same shape you are going to see for the next half of the period. Yes or no? Okay. And here this average value of this signal is going to be 0. So this pattern is going to get repeated here. This is nothing but what? This is nothing but a periodic signal. Yes or no? This is nothing but a periodic signal. So it is going to repeat itself. Right. So this is the property of what? This is the property of pure AC signal. If you consider voltage signal here, if you consider voltage signal, its polarity is changing with respect to time. So similarly, if you try to draw the current signal, okay. So what you can say for current signal here? During positive half cycle, the direction of the flow of current, is in one direction, and during next half cycle, the direction of flow of current is changing. It is going to flow in opposite direction. Yes or no? It is depending upon what? It is depending upon the polarity of the voltage signal. If the polarity of the voltage signal is positive, in that case, it is going to drive the current in the circuit in one direction. Whenever the polarity of the voltage signal is changing, then it is going to drive the current in the circuit in opposite direction. Right. So these are the properties of what? These are the properties of pure AC signal, and there will be no DC component here. There will be no DC component that is present in this signal. Okay. Now I want to convert this pure AC signal into what? Into pure DC signal. Why I want to convert pure AC signal to pure DC signal here? Because if you observe the main power supply here, so from our plug point, whatever it may be, okay. So what you are going to get here? You are going to get pure AC signal. Yes or no? So the RMS voltage is around 230 or something. Right. Okay. So you are going to get a pure AC signal from our main power supply. Right. So, but whatever the electronic devices that we are using, suppose let us say desktop, laptop, okay, so or a mobile phone, whatever the electronic devices that you are using in home, okay, almost most of the components that we are using in our home are going to operate with what? Are going to operate with DCR. They need DC voltages and DC currents. They need what here? DC voltages and DC currents. But from our main supply, we are going to get pure AC signal. Okay. So if you supply that pure AC signal to the electronic devices, they are not going to operate here because it is fluctuating. Yes or no? It is fluctuating for each and every half period of time. Okay, so that's why they are not going to operate with that ACR. They need some DC voltage and DC current to operate. So that's why we have to convert this pure AC signal into what? Into pure DC signal in order to operate the components that are present in our devices, that are present in our home. Okay, like mobiles or desktops or laptops, whatever it may be. Okay, okay, yeah. So that is the need here. That's why we want to convert pure AC into pure DC. So what I have said, pure DC signal here, it is having two properties. What is first one here? Its polarity. If I am talking about voltage signal, pure voltage signal, that is a pure DC voltage. What is its property? What I have told here? So the polarity of the signal, must remain same. Yes or no? The polarity of the signal must remain same with respect to what? With respect to time. This is the first property I have told. And what is the next property I have told for a pure DC voltage? What is the next property? So the voltage must be constant with respect to what? With respect to time. So these two properties it has to satisfy. So if I am talking about pure AC, pure DC current here, okay, so then it has to satisfy the direction of current here. The direction of current must remain same, remain same with respect to time. That means the current has to flow only in one direction, or you can say current is what? Current is unidirectional. Current is unidirectional. It has to flow only in one direction, right? And the current must be what? Current must be constant. Current must be constant with respect to what? With respect to time. Yes or no? So these are the things I have explained in the previous sessions here. So this is the need here. This is the pure AC signal. In it, the DC component is 0 here. We want to convert this pure AC signal into pure DC signal, in which the AC component must be equal to what? AC component must be equal to 0. Pure DC signal means AC component must be equal to what? AC component must be equal to 0. Here DC component must be equal to 0. So we want to convert this pure AC signal into pure DC signal. Yes or no? Okay, so here we are not having any DC component here, but at the output we want the total signal as a DC signal, right? Okay, so we are having nowhere you are having DC. We are trying to convert this total AC into what? Into pure DC. Okay, so we have to design that type of circuit. We have to design that type of circuit which is going to convert this pure AC into pure DC. Okay, so how we are going to do that? See here. How we are going to do that? See here. Now, so here this is main power supply here. Here I am having main power supply. Yes or no? Main power supply. Okay, so here you are going to have a pure AC signal, right? It is going to have pure AC signal. It is going to give you pure AC signal. So the voltage here is approximately 230, around 230 volt RMS. Yes or no? 230 volt RMS. So this is the main power supply. Now here, whatever the devices that we are using here, they don't need huge amounts of voltages and currents here. If you take your mobile phone or something, or laptop or something, they need what here? Very less amount of what? Maybe 1 volt or 0.5 volts or 2 volts, like that DC voltage they need. Okay, they don't need huge amounts of DC voltages and currents. They need the currents in terms of milliamperes or amperes maximum, and the DC voltage will be 1 volt or 2 volts, like that. Okay, so we need very less voltages of we need very less DC voltages and less DC currents here. We don't want a huge magnitudes of DC voltages and currents. Okay, but here you are having the RMS voltage is 230 volts here. RMS voltage is 230 volts, right? Okay, so we don't need, if you convert this directly to DC, the total voltage, you are going to get huge amount of DC voltage here. We don't want that much of DC voltage. So for that, what we are going to do here is, we have to step down this voltage. We don't want this much of voltage here. Suppose I want only 8 volt RMS. I want only 8 volt RMS. I don't need 230 volt RMS value. So then what I can do here? I have to step down this voltage. I have to step down this voltage to 8 volt RMS. So that means I have to use what here? I have to use a step down transformer, right? Yes or no? So here in this block, I have to use what here? I have to use, first of all, a step down transformer. Step down transformer. I have to use step down transformer, right? Okay. Now at the output of this step down transformer here, at the output of this step down transformer, what you are going to get? Still it is going to be AC signal only. Still it is going to be pure AC signal, but its voltage will become what here? 8 volt RMS. Okay. So I have taken some rough value here. It is not compulsory 8 volt RMS. Just for example, I am saying. Okay. So this is pure AC. Still it is pure AC. Here also you are going to get still pure AC signal, but okay, so let us say this is 8 volt RMS value or something. Okay, okay, still it is pure AC. Still it is pure AC, right? Okay. Now what I am going to do here is, I'm going to connect, I'm going to give this input, I'm going to give this input to, see, the property of DC signal, the property of DC signal is what? The polarity of the signal, the polarity of the signal must remain what? Must remain same with respect to time, and the voltage must be, that means the signal must be constant with respect to time. It has to satisfy these two properties here. For pure DC signal, for pure DC signal, it has to satisfy these two. The polarity must be same, and the signal must be constant with respect to time. Okay. So now here, if I connect this here, if I connect this to a, I am connecting this to a full wave rectifier here. Let us assume I am connecting this to a full wave rectifier, full wave rectifier. So what it is going to produce here? Full wave rectifier. See, the transfer characteristic of full wave rectifier will be like this. Ideal characteristic here. I am drawing ideal characteristic. So this is output and this is input. So that means output is equal to what? Output is equal to some k times of input, and here in this region output is equal to minus k times of what? Input. Okay. So that means whenever input is positive, output will be exact replica of the input, and whenever input is negative, output will become what? Minus k times of input. So input is negative and here minus is present, minus into minus will become plus. Yes or no? So that means negative polarity will also converted into positive polarity. So positive polarity will be replicated at the output, and negative polarity will also, negative polarity of the signal will also converted to what? Positive polarity. So at the output here, at the output, you are going to get what? You are going to get, now here the signal is bidirectional, yes or no? That means it is having both polarities, positive and negative, yes or no? Pure AC signal. Now here at the output, what you are going to get here? At the output, you are going to get what? You are going to get the waveform like this, yes or no? Okay. So negative, positive half cycle will be replicated as it is, and negative half cycle will also convert it to what? Positive side, positive polarity, yes or no? So this is the output waveform we are going to get here for full wave rectifier, for full wave rectifier. Now here we have achieved the first property of the DC signal. What is the first property of the DC signal here? The direction, see, the polarity of the signal must remain what? Must remain same with respect to time. Must remain same with respect to time. Now here, if you observe for this signal, over a duration of time here, for all the time, the polarity of the voltage is plus or not, positive or not? That means it is same, yes or no? Okay. So the polarity is remaining same throughout the time. That means you have achieved one of the properties of DC signal. But still here the signal is changing with respect to time. Still the signal is changing with respect to time, but its polarity will be same here. Only one polarity is present, yes or no? Okay. So it is not bidirectional, right? Okay. Okay. So that's why still it has satisfied one of the properties of the DC signal, that is now it has become unipolar, right? But what is happening? Still it is varying with respect to time. So that's why we call it as what? We call it as pulsating DC. So why we are calling it as DC here? Because now the signal has become unidirectional or unipolar. If you are talking with respect to voltage, you have to say unipolar. If you are talking with respect to current, you have to say unidirectional. Yes or no? So if the voltage is unipolar, it is going to make the current unidirectional, right? Okay. Okay, yeah. So pulsating DC, because why we are calling it as DC here? Because now the signal is having only one polarity, that's why we are calling it as DC, but it is not constant with respect to time, it is pulsating or changing with respect to time, that's why we are calling it as pulsating DC. So that means this signal is going to have, still it is going to have both what? Both AC component as well as what? DC component. It is not pure DC, it is not pure AC, it is a mixture of what? Both AC and DC, right? Okay. Now here one more thing we have to observe here is, I have also explained in the previous sessions about the differences between linear circuits and non-linear circuits, right? Okay. So you can go through that here, So here, see here you are having pure AC signal here, that means it is going to have what? Only one frequency component. Let us say that frequency component is F0, let us assume. Okay. Now here at the output here, at the output, okay. So at the output, what you are getting here, what you are getting, you are not getting a pure AC signal, you are not getting a pure AC signal, you are getting some pulsating DC. So here the output is distorted, yes or no, the output is distorted from the input or not, yes or no here. So that means this full wave rectifier is what, a non-linear circuit or not, yes or no. That's what I have said here. Whenever you are dealing with the non-linear circuit, okay, so the output cannot be what, the output cannot be exact replica of the input, output is going to get distorted. Whenever you are operating the circuit in non-linear region, output is going to get distorted from the input, right, okay. So this signal is distorted, it is not exact replica of the input, okay. So because of the non-linearity involved in this rectifier circuit, right, okay. So whenever you are dealing with non-linear circuits here, what I have said here, why we are getting this distortion, because they are going to generate what, they are going to generate harmonic frequencies here, they are going to generate what here, harmonic frequencies, right, okay. So harmonic frequencies means what here, they are in general, they are higher harmonic frequencies here, like you are going to have some fundamental frequency, okay. So the integer multiples of that fundamental frequency components are called as what, harmonic frequency components. So this, whenever you are dealing with non-linear circuit, or whenever you are operating the circuit in non-linear region, it is going to generate what here, it is going to generate the harmonic frequency components, which is going to have higher frequency components, right. Harmonic frequency components means what, they are integer multiples of fundamental frequency components. That means here if you are having f0, it is going to generate 2f0, 3f0, 5f, 4f0, 5f0 and so on, like that, okay. So all these are nothing but what, higher frequency components. So adding all these components together, okay, you are going to get finally a distorted output waveform in this manner. So that means this signal is made up of what, is made up of this harmonic frequency components, this harmonic frequency components, yes or no. Now here you are having all the higher frequency components, yes or no, okay. So now we try to eliminate this frequency components here. See what we have to do, pure DC signal, our aim is to generate pure DC signal. That means in pure DC signal there should not be any frequency components, right. The frequency of that signal must be equal to 0. But here we are having many frequency components here, all the higher order frequency components are present in this signal, right. So we have to eliminate all these higher frequency components. So what must be the next stage here, tell me? We want to eliminate all the higher frequency components. So what you have to do, you can use what, you can use filters or not, yes or no. So what is the purpose of filters? They can eliminate what, they can eliminate the unwanted frequency components, right. Here we want to eliminate the higher frequency components. That means you have to design what, you can design a low pass filter, right. So low pass filter, with the help of low pass filter you can attenuate all the higher frequency components, right, okay. So the next section here, the next section, you have to connect what here, you have to connect a filter circuit, you have to connect a filter circuit. So in general it is nothing but what here, in general it is nothing but low pass filter here, it is nothing but low pass filter in general, okay. We want to eliminate all the higher frequency components that are present in this signal, okay. So that's why we are going to use filter circuit. In general this filter circuit is a low pass filter, right. See one simple thing here, if you are having, so this is the output, this is the input to the filter signal, yes or no. So here you are having, whenever you are using filter circuit, let us assume, see here, I will give you one simple example here, okay. If you are having some full wave rectifier circuit like this, okay. So here at the output you are having AC plus what, AC plus DC. So this signal is having both AC components as well as DC component. So now here what I am going to do here is, if I connect some capacitor here, if I connect some capacitor across this one, and here you are having load resistance, here you are having load resistance, okay. If I connect in this manner for the output, at the output of full wave rectifier, let us assume, okay, then what will happen here, what is the property of a capacitor, what is the property of a capacitor, what capacitor will do, capacitor is going to allow AC and blocks DC, yes or no. Now here at the input you are having both AC as well as what, as well as DC. So what capacitor will do, capacitor is going to allow AC, and it is going to block what? It is going to block DC, right? So that means that AC signal is going to flow through what? It is going to allow the AC signal, and whatever that is left out, that is nothing but what? That is going to be DC signal. But actually speaking, what is the impedance? What is the impedance offered by a capacitor here? The impedance offered by a capacitor is going to depend upon what? Is going to depend upon frequency, right? The impedance offered by a capacitor is equal to what? Is equal to 1 by j omega c, 1 by j omega c. Okay, so yes or no here? Okay, so for low frequency components here, for low frequency components, that means if omega is less, then the impedance offered by the capacitor is more. The impedance offered by the capacitor is more. Okay, so that means if you take DC signal here, if you take DC signal, then omega will be 0. It is going to offer infinite impedance. That means it cannot allow DC. It cannot allow DC. Okay, but if the frequency is very lower, for low frequency signals also, it is going to what? It is going to offer very high impedance, That means it cannot allow, actually speaking, it cannot allow very low frequency signal components also. But as the frequency goes on increases, the impedance offered by the capacitor will be very low. That means it is going to allow what? It is going to allow high frequency components. But it cannot allow what? It is going to block low frequency components. Yes or no? Because for low frequency signals, the impedance offered by the capacitor is very high. Okay, so that means the output, whatever that you are getting here, it is going to have still DC plus what? DC plus AC, but here AC is nothing but it is going to have what? It is going to have only low frequency components, But here this AC is going to have both low frequency components plus what? High frequency components. Both are going to be present at the input. But as coming to the output, still you are having DC as well as what? AC, that is having only low frequency components. Now you have to attenuate or eliminate those low frequency components also. Yes or no here? Okay, so in general you cannot get a pure DC signal out of the filter here, Still there exists some AC component with DC component, right? So you have to eliminate that AC voltage also. You have to eliminate that low frequency AC components also. So for that what we are going to do here is, so here at the output of filter here, you are going to get what here? You are going to get a ripple voltage here. You are going to get a low frequency component of the signal, DC plus AC. Okay, so AC is low frequency component. So combining these two, you are going to get some ripple voltage or ripple signal like this here, something. Okay, so this from here to here, we call it as ripple voltage. Here. The distance from here to here is nothing but ripple voltage. So the output of filter here, is not a pure DC. Still it is having some ripple. So the voltage fluctuations is still present or not? The voltage fluctuations is still present. So let us say this is V maximum and let us say this is V minimum. So still the voltage is fluctuating between V maximum and V minimum like this. Right? Okay, so you are having the variations, at the output of filter. So now in order to eliminate these ripples here, and to produce a constant voltage, DC voltage at the output, what you have to do? What is the next stage you have to do? Yes or no? What is the next stage you have to do? Tell me. Okay, what is the next stage you have to do? Tell me here. See here, what you can do? Tell me. See, now here we know that ZNR diode here. We know ZNR diode or not? Okay, I hope you are having at least some minimum idea about the ZNR diode. Now, if I apply this ripple voltage here, this is nothing but what? This is nothing but some ripple voltage. Right? So now I am going to apply this ripple voltage signal. I am going to take this ripple voltage signal here. This is V ripple. So that means it is going to vary. From some V maximum to V minimum, some V maximum to V minimum. It is going to vary between V maximum to V minimum, some ripple voltage. So what I am going to do here is, I am going to apply this to this circuit here. So here I am using some Zener diode, right? So here this is nothing but load here, this is nothing but load, right? Okay, so now here this ripple voltage here, V max to V minimum, is nothing but some ripple voltage. So this ripple voltage, here you are having ripple voltage, here resistor. Okay, now here you have to operate this Zener diode here, you have to operate this Zener diode in breakdown region, So what happens if you operate the Zener diode in breakdown region here? See, if you observe the characteristic here, if you observe the diode characteristic, so here this is VD you are having, and here ID. Okay, so I am drawing only in this region here. See here, so here you are going to have almost zero, and suddenly the current will start increasing. Yes or no? Okay, so this region here, this is called as breakdown voltage. This is called as what here? Breakdown voltage. So what is the advantage of this breakdown voltage? That means why we are operating the Zener diode in breakdown voltage. Okay, see here what is the purpose means. See, so this is the minimum current here, this is the minimum current through Zener diode, and we can fix maximum current here, maximum current. Okay, so this is the minimum current that has to pass through Zener diode whenever it is operating in breakdown region. That means whenever it starts operating in breakdown region, at least the minimum current that has to flow through the Zener diode must be I minimum, and the maximum current that can flow through the Zener diode is I maximum. So what I have said here, for any device here, for any device, it is going to have some power handling capability. Yes or no? Power handling limit. Okay, so you should not cross that power limiting capability of the device. Yes or no? So if you go beyond that power limits, what will happen here? The heat dissipation across the device will be very, very high, and the device cannot tolerate that much of heat, and it will get burned away. Right? Okay, so always you have to operating region must be specified here. For any device, operating region must be specified. You should not go beyond that limits, right? Okay, so this is the maximum current that can flow through Zener diode, and this is the minimum current that can flow through Zener diode. And for this fluctuation of current here, from minimum to maximum, it is going to maintain the constant voltage. So that is the beauty of this Zener diode here. We are going to specifically design this Zener diode in such a way that it can sustain, or it can operate only in breakdown region. It can operate in breakdown region also. If you are using normal diode, it cannot be operated. It is not designed in such a way that it cannot be operated in breakdown region. So in order to operate in breakdown region, we have to design a separate diode that is called as Zener diode, and it cannot operate throughout this breakdown region here. There is a limit, that is the minimum current that has to flow through Zener diode is I minimum, and maximum current that can flow through Zener diode is I maximum. Understood? Okay, so whenever it is in this limits, see, if it is less than I minimum here, you cannot say the diode is in breakdown region, the Zener diode is in breakdown region. For the Zener diode to operate in breakdown region, the currents that has to flow through them is minimum is I minimum and maximum is I maximum, right? Okay, so what is the beauty of this Zener diode is, even there is a fluctuation of current, from I minimum to I maximum, it is going to provide the constant voltage here. So that is the beauty of this Zener diode. Okay, so here, but you have to operate this Zener diode always in what? Always in breakdown region. So what is the beauty means here, why we are getting the fluctuations in current here in a circuit? Whenever the voltage that you have applied here, the ripple voltage whatever you have applied. So this voltage is fluctuating between V maximum and V minimum. That means whatever the current that it is going to pump here, whatever the current that is going to pump, it is also going to vary or not? It is also going to vary, because here the voltage is fluctuating between some V maxima to V minima, and hence whatever the current it is going to produce, that is also going to fluctuate, from I maximum to I minimum or something. Yes or no? Okay, it is also going to fluctuate. So whatever the fluctuations in current here, it is going to allow the fluctuations in current through Zener diode. It can allow the current fluctuations in current through Zener diode, and it is going to maintain what? It is going to maintain the constant voltage at the output. Here VZ means output is also at what? Output will be also at what? Output will also, you are going to have same VZ. Yes or no? These two are in parallel. Right, okay, but one thing you have to remember is whenever you are operating with Zener diode, you have to maintain the Zener diode, to operate in breakdown region. Okay, if the current in the circuit becomes less than I minimum, then it cannot go to breakdown. If the current in the circuit or the current that is flowing through the Zener diode will become greater than I max, then it cannot sustain. Okay, so it will get damaged. Right, okay, so whatever the fluctuations in the voltage here, because of these fluctuations you are going to get the fluctuations in the current. So even though there is a fluctuation in current, that variation in current, this Zener diode will allow, and even though there is a fluctuation in current, it is going to maintain what? It is going to maintain it is going to give you the constant voltage at the output, because we made that Zener diode to operate in breakdown region, and hence it is going to produce a constant voltage at the load. Right, okay, so that means this circuit we call it as what here? This circuit we call it as what? We call it as voltage regulator. This circuit we call it as what? Voltage regulator. So you can apply this ripple voltage to a voltage regulator circuit in order to produce what? In order to produce a constant DC voltage. See, we can design the regulator circuits not only with Zener diodes here. You can design by using op-amp circuits also. Okay, op-amps, transistors. By using transistor or op-amp circuit, you can design a better voltage regulator circuits also. Okay, here I have taken one simple example to explain why we are using this regulator circuit. Okay, so here this is the ripple voltage here, this is the ripple voltage. Now you have to apply this ripple voltage to what here? Next section is nothing but what? Is nothing but voltage regulator. It is nothing but voltage regulator, right? So we have to use voltage regulator circuit. So now here, so what is the output of voltage regulator circuit here? What is the output you are going to get? So even though there is a fluctuations, it is going to give you a constant output voltage. So at the output here, you are going to get what? You are going to get, so this is T, let us say this is V. Okay, so it is going to give you a constant voltage, right? Okay, now here at the output, this is the output of the voltage regulator. So let us say it may be 1 volt or 2 volts or something. You may get 1 volt or 2 volt or something. You have produced some DC voltage. Now here you can connect what? You can connect your load here. Here you can connect your load. That means you can connect your mobile phone, or you can connect your laptop or computer, whatever it may be. Okay, so it is going to operate with this DC voltage. So finally you are providing this DC voltage to the load here. Okay, so this whole setup, what it is doing here, it is converting pure AC signal. It is converting pure AC signal into what? Into pure DC signal. Pure AC signal into what? Into pure DC signal. Here the DC component is equal to 0 at the initial stage, and finally the AC component in the signal is equal to 0. So that is the beauty of this circuit here. It has converted the total pure AC signal into pure DC signal, right? Okay, so this is the purpose of this circuit here, So this circuit is having many stages, right? Okay, so main power supply here, step down transformer, full wave rectifier, and then filter, and then voltage regulator. So here first we are going to study about this rectifier circuits here. This stage we are going to study. Okay, rectifier circuits. Then we can go for filter circuits, and then we can go for voltage regulators. Okay, okay, yeah. So is it clear here up till now? Yes or no? So I hope it is clear here. I hope it is clear. Is it clear here? Tell me here. Yes, yes here, it is useful for gate aspirants also. It is not only for IES here. See, whenever whenever we are dealing with core subjects like analog electronics or EMT or whatever may be the subject here, they are present for both IES as well as what? As well as gate also. Yes or no? It is going to be helpful for both gate as well as IES or any other competitive exams like ISRO, whatever it may be. Okay, so for all the exams, the concepts are going to remain same now. It is not going to change. Only the pattern of the exam is changing, right? Okay, so learn the concepts, and according to the pattern, if you want to follow that pattern, you have to practice the previous questions that are given in that particular exam. Then you can adopt that pattern here. Okay, so that's the only thing you have to practice. Concept wise, we can we will provide all the concepts clearly, right? Okay, it is our duty to provide the concepts clearly, and based on this also we are going to solve some problems here. Based on this also we are going to solve some problems also. So it is going to be very much helpful for both as well as IES and gate here. Okay, okay, yeah, fine. Okay, yeah. So first we will try to design half wave rectifier here. It is in general we are not going to use this half wave rectifiers here. We are going to use full wave rectifier circuit only, but this is going to give you some basic understanding of rectifier circuit. Okay, so first we will start with half wave rectifier, then we will go for and we will solve some problems based on this half wave rectifier. Okay, so then we will go for full wave rectifier, and we are going to solve some problems on full wave rectifier circuit also. Okay, so but today I am ending the session with this here. So tomorrow we are going to start half wave rectifier, and also we will see full wave rectifier, and also we try to solve some problems here, right? Okay, so in the next session we try to solve some more problems. So with this I am winding up the session here. With this I am winding up the session for today. So tomorrow we are going to start some problems here. We are going to start doing some problems based on this rectifier circuits. So they are very simple here. I will explain, okay, in the next session, and also we are going to solve some problems here, right? So with this I am winding up the session here. Okay, so we will meet tomorrow. Okay, thank you here. Thank you. Take care. Bye bye.